Hello everyone, welcome to this next lecture in the Neural Networks from Scratch series. In this lecture, we are going to essentially cover three things. The first thing is derivatives, the second is gradients, partial derivatives, and the final thing is chain rules. So, if you are already familiar with derivatives, gradient, partial derivative, and chain rule, you can feel free to skip this video. However, if you need to refresh the calculus needed to understand neural networks, this one lecture will go through all the key concepts which are needed. There is a reason why many people say that calculus is the building block of understanding backpropagation, and I've deliberately created this lecture so that before we start with backpropagation, which is essentially taking the gradient of the or the derivative of the loss function with respect to the weights and biases of the neural network, I want to make sure that all of you are aware and your foundations are clear about these calculus concepts. So let's start with the first concept, which is derivatives. So the reason we care about derivatives is because if you want to adapt the weights and biases so that the loss function decreases, we first need to understand the impact of weights and biases on the loss function itself so that we can change them such that the loss function reduces. If we do not know how the weights and biases impact the loss function, it will be very difficult for us to know how to change them. So, if you consider two quantities x and y, we need to know the impact of x on y, or rather, we need to know the impact of delta x on delta y, which means the change in x on the change in y. And this exact quantity, the impact of change in x on change in y, can be calculated if you know the derivative of a function. So let us look at this further, how to find the impact of a parameter or input on the output. And through this, we will also understand the concept of derivatives. First, I am going to take a linear function f of x equal to 2x, and I've plotted this over here right now. So if you find the slope of this function at every single time point, let's say if I take first point as 1 comma 2 and the second point as 2 comma 4, the slope of this function uh, at any point essentially is given by y2 minus y1 divided by x2 minus x1. So let me do this, 4 minus 2 divided by 2 minus 1, so that will be equal to 2. So if you find the slope of this function at any point along this line, it's essentially constant and it will have a magnitude of 2. Okay. Now let us look at f of x equal to 2x square, which looks like this. It's a parabola shape. And now if I ask you to find the slope of the function at every point, let us see first qualitatively how the slope changes. At x equal to 0, it's a flat line, right? The slope. So the slope is 0 here. Then slowly the slope starts to increase. As my x becomes more large, my slope becomes even steeper and steeper and steeper. So in fact, as the x coordinate increases, you will see that the slope becomes higher and higher and higher. And how am I making this intuitive prediction? Because I'm looking at this tangent to a particular point. So whenever I say find the slope, just look at the tangent at that particular point and draw that tangent and look at how steep that tangent is. If the tangent is flat, like it is at x equal to 0, it means the slope is 0. If the tangent is slightly inclined, it's a higher slope. If the tangent is vertical, it's a infinite slope. So if you look at this line over here, this straight line, it has infinite slope. So from a horizontal line to vertical line, the slope changes from 0 to infinity. Now, if you look at this function and if you try to find its slope at every single point, you will see that as x increases, the line becomes steeper and steeper and steeper. In fact, if you extend this even further, the slope becomes steeper and steeper and steeper. Whereas here, if you see in the linear line, if you draw the tangent at any point, it's essentially along this line itself, and it makes the same angle with the horizontal, and hence the slope is constant. So, if you measure the slope of the tangent line at any point, it actually gives you the impact which x has on y. So, let's say if you take this function again, and if you want to see what is the impact of the change in this point x, which is x equal to 0, on y, you will just take the tangent at this point and you will see the slope is 0, which means the even if I move slightly, even if I move slightly in this direction, right direction, or the left direction, the y value is not going to change much. So a small increase or decrease x, or a small change in x, is not going to lead to too much change in y when x equal to 0. However, if you go on increasing x, so if x equal to here, then if you look at the tangent, the slope is higher. This means that if I take a small change in x in either direction, it will lead to a greater change in y compared to x equal to 0. Whereas if I take a very high x, if I take, let's say, x equal to 5, and again I look at delta x, which is a small change in x, the line here, the slope will be even steeper. So a small change in x will lead to an even higher or a much larger change in y. So the slope of a function at a particular point, the slope, or rather the slope of the tangent line, the slope of a tangent line at a particular point x gives us an indication of the impact which a change in x has on the change in y. So it tells us that if I have a small change in x, delta x, how much it is going to affect delta y. And you see, this is exactly what we started with at the beginning of the lecture. We need to know the impact of delta x on delta y. So now we have a quantity which can give us that impact. You have a function, you just find the slope of a tangent line at a point, and that will give you that if you move slightly to the left or slightly to the right, how much does y change? Which means what's the impact of that particular point x on the output? Or rather, what's the impact of the change in x on the output? It turns out that for any function, there is a way to calculate this slope of the tangent line at any point, and that is actually called as the derivative of the function at that point, and it is defined by the notation d by dx. So if you have any polynomial, let's say if you have polynomial a into x raised to n, its derivative is given by a into n into x raised to n minus 1. So if you have this x, then its derivative will be given by 1 into x raised to 0, which is 1. If you have a function as x square, its derivative will be given by 2x. If you have a function x cube plus 2x square plus 6, its derivative will be given as 3x square plus 4x. Another rule which a derivative follows is that if there are two functions f of x plus g of x, the derivative of the combined function is the derivative of the first function plus derivative of the second function. So if you look at the summation of functions here, x cube plus 2x square plus 6, if I want to find the derivative of this combined function, I just find the derivative of the first, which is 3x square, add it to the derivative of the second, which is 4x, and add it to the derivative of the third. Remember that the derivative of a constant is always 0. And to get an intuition for this, always try to visualize the graph. So for a constant function, the graph will always look like this, right? So if you find the slope at any point, it's always a horizontal line. So the slope is 0. Um, and the derivative of a function is also denoted by a notation f dash of x. So f of x is the function itself, and f dash of x is the derivative of the function. So for the first function here, f dash of x equal to 1. For the second function, f dash of x equal to 2x. For this third function, f dash of x equal to 3x square plus 4x. Remember that this is not intended to be a course on calculus, so I'm briefly explaining you the derivative formulas. But if you really want to go into depth, I encourage you to take some basic calculus courses which can explain about derivatives in a lot more detail. However, for the purposes of following this course, this much knowledge is enough for derivatives of simple functions. Now we look at the second part of this lecture, in which we'll be talking about gradients, partial derivatives, and chain rule. So up till now we only looked at functions of one variable. There was y, which was the dependent variable, and there was x, which was the independent variable. And we tried to see how change of x led to a change of y, right? But what if the function itself was, let's say, f is a function of x, y, and z? Then how do you find the derivatives with respect to x, y, and z? How do you even represent it? Because if you just write f dash of x, y, and z, the question is that, okay, this denotes a change in f, but with respect to change in what? Remember, for just one function, f dash of x denotes the change in y with respect to change in x. But if you just write f dash of x, it's very vague because you don't know whether it's change in the function f with respect to change in x or y or z. That's why for functions of multiple variables, there is this idea of partial derivatives, which basically gives you the impact of every single input on the function output. So impact of x on f, or change of x on change in f, change of y on change in f, and change of z on the change in f. So we'll look at gradients also, and finally we'll look at the chain rule, which is essentially the backbone of backpropagation. So first, I want to introduce you to the notation of partial derivatives. So as I said, we cannot have f dash randomly because we need to specify we are taking the derivative with respect to which variable. So the notation is this, and so henceforth in this series, when I say d by dx, I mean normal derivative, and when I say dou by dou x, I mean partial derivative. So if I represent dou by dou x of f, it means the partial derivative of f with respect to x. So partial derivative of f with respect to x, which means what is the impact of the change in x on change in f. If I write dou f by dou y, it is the partial derivative of f with respect to y, which means what is the impact of change in y on the change in f. And if I write dou f by dou z, it means the partial derivative of f with respect to z, which is essentially, so partial derivative of f with respect to z, which is essentially what is the impact of a change in x on the change in f. So this is the notation for partial derivative. Now let's see how to compute partial derivative. It's actually very simple. The simple trick is that you just ignore the other variables. So for example, or rather you just treat the other variables as constants. So if my f is 2x plus 3y square, and if I want to take the partial derivative of f with respect to x, I will treat y as a constant. So, and you know that the derivative of any constant with respect to x will be 0, right? So if I take the partial derivative of f with respect to x, this will be the partial derivative with respect to partial derivative of x, partial derivative of 2x with respect to x, plus the partial derivative of 3y square with respect to x. Now, y is another independent variable. So you can treat this as a constant when you take the derivative with respect to x. So then this will be 0 because y does not depend on x. Both of them are independent variables. So this term would be 0. So the only thing which will survive is the derivative of 2x with respect to x. And we have already seen how to calculate that when we looked at derivatives. So this will be equal to 2. When you want to calculate the partial derivative of f with respect to y, it will be the partial derivative of 2x with respect to y plus partial derivative of 3y square with respect to y. Now, the trick which I mentioned before. If you are taking partial derivative with respect to y, all other variables need to be taken as constants. So this will be taken as a constant, and derivative of a constant with respect to y will be 0. So the only thing which will survive is the derivative of 3y square with respect to y, and that will be 6y. So if you look at f, the partial derivative of f with respect to x is 2, and the partial derivative of f with respect to y is 6y. What this means is that what is the meaning of these two derivatives, right? Here we saw that in one dimension the meaning of the derivative was equal to slope. If you look at this function f of x equal to 2x plus 3y square, and if you plot it, it will actually be a three-dimensional function. So if you take the slope of a three-dimensional function, it will actually slope in two sides. It will slope along x and it will slope along y. So it has two slopes. So when you calculate the slope, you need to specify along which direction are you calculating the slope. So dou f by dou x is the slope along the x direction, and dou f by dou y is the slope along the y direction. So if you plot the three-dimensional function, it will look like a parabola but in three dimensions. And the actual gradient will be a vector summation of derivative with respect to x and derivative with respect to y. So the actual gradient will be a vector summation of these two gradients. So that's why we have to take two gradients here, because the slope will have slope in x and slope in y. If there are three variables, we need to take three partial derivatives. Okay, so as I mentioned, three variables. Let's take an example of three variables here, which is a bit complex since there is a product term. But remember our trick. When you take the partial derivative with respect to one variable, all other variables will be treated as constant. So let's say this is f of x, y and z, 3x cube z minus y square plus 5z plus 2yz. If you take the partial derivative of f with respect to x, it will be the partial derivative with respect to the first term plus the partial derivative with respect to the second, third and fourth term. Now remember, the second, third and fourth term does not have x. So these will be treated as constants. So their derivative with respect to x will be 0. In the first term, 3 and z will also be taken as constants because we are taking the partial derivative with respect to x. So when you take the derivative of 3x cube z, 3 and z will be taken as constants. So they'll come out of this. So then the only thing which remains is the derivative with respect to x cube, and that is 3x square. So the partial derivative of f with respect to x will be 3z into 3x square, which is equal to 9x square z. And I want to take one more example just to motivate this idea further. If f of x comma y is the maximum of x and y, let's say if that's the function. So if x is 2 and y is 3, f will be 3. If x is 2 and y is 4, f will be 4. If x is 4 and y is 2, f will be 4. So it will just take the maximum of x and y. So what is the partial derivative of f with respect to x? If x is greater than y, this will be just x. If x is greater than y, and if y is greater than x, it will be y. So if x is less than y, then it will be y. So if you take the partial derivative, if x is greater than y, it will just be 1, and if x is less than y, then it will be 0, because the partial derivative of y with respect to x is 0. You just have to treat y as a constant. So the answer is, if x is greater than y, this will be equal to 1. It will be 0 if x is less than y. A special case of this is when f of x comma y is maximum of x and 0. And the reason I'm taking it is because it is exactly what happens in ReLU activation function. So if you take the partial derivative of this with respect to x, it will essentially be 1 if x is greater than 0, and it will be 0 if x is less than 0. So it's exactly same as this case, you just have to replace y with a 0. So this is the meaning of partial derivatives. The way they operate is exactly similar to normal derivatives if you remember the trick. The trick is that if you take partial derivative with respect to one variable, the other variables can be treated as a constant. Why will we need partial derivatives in neural networks? Because we will have a function of a huge number of parameters. all the weights will be treated as separate parameters. All the biases will be treated as separate parameters. So we will have a function of a huge number of variables. So we will need to know how to take the gradient or the derivative of the loss function with respect to each of these variables. That's why we need to have an intuitive understanding of partial derivatives. Um, okay, and now we will cover the gradient. After learning partial derivatives, understanding the gradient becomes very easy. So if you have a function of three variables x, y, and z as 3x cube z minus y square plus 5z plus 2yz, if you take the partial derivative with respect to x, you will get 9x square z. If you take the partial derivative of y, you will get minus 2y plus 2z. And if you take partial derivative with respect to z, you will get 3x cube plus 5 plus 2y. Now the gradient is just the vector of all possible partial derivatives. So the gradient can be written as a vector like this. It has three rows and one column. The first element is partial derivative with respect to x. The second element is derivative with respect to y. And third element is partial derivative with respect to z. So if someone asks you what is the gradient of this function f, you can just say that it's a vector whose first value will be dou f by dou x, which is 9x square z. Second value will be dou f by dou y, which is minus 2y plus 2z. And the third value will be dou f by dou z, which is 3x cube plus 5 plus 2y. So the gradient actually is a vector which contains the direction of the steepest ascent. So let's say if you have a three-dimensional function, the gradient gives you the direction in which the function will increase the most. So it turns out the negative gradient is the direction where the function decreases the most. And why we care about the gradient is because we eventually want to move in a direction where function decreases the most, right? Let's say this is the loss function, and if we are here, we want to move in a direction of steepest descent. So remember, the gradient gives us the direction of steepest ascent, which will be in this direction, grad f. However, negative of grad f will give us the direction of steepest descent. So this negative of grad f is the direction which we will need to go when minimizing the loss function. And that is why we are learning about the gradient right now. When we look at back propagation, this loss will be a multi-dimensional loss function of weights, biases, etc. But the underlying philosophy is the same. You just calculate the gradient of this loss function and then move in the direction of the negative gradient. Okay, so this is the explanation of gradient. Initially, I thought I'll cover the chain rule also in this lecture, but I think the lecture will become a bit long. So I'll cover it in the next lecture. Just as a recap, in this lecture, we looked at first partial derivatives. First, we looked at normal derivatives. So we looked at polynomials a into x raised to n and saw that the derivatives is n into a into x raised to n minus 1. And the visual understanding of this is that it's given by the slope at a particular point. Now, if we have function of multiple variables, such as this function here, we have to look at partial derivatives. The trick of partial derivatives is that when you take partial derivative with respect to one variable, the other variable can be imagined to be constant. So dou f by dou x, which is the symbolic representation of partial derivative of f with respect to x, will just be derivative of x with respect to x. So this will be 1, and dou f by dou I will be also equal to 1. If you have the function as x into y, dou f by dou x will be y, because y will be treated as a constant, and dou f by dou y will be x, because x will be treated as a constant. If the function is f of x comma y is max of x comma y, dou f by dou x will be 1 if x greater than y and 0 otherwise. Whereas if the function f of x comma y is max of x comma 0, which is what happens in a ReLU activation function, then dou f by dou x is 1 if x is greater than 0 and it's 0 otherwise. So I hope you have understood the concepts of derivatives, partial derivatives and gradient. In the next lecture, we'll be looking in detail about the chain rule, and we'll understand it because it is the backbone of back propagation. So thank you so much everyone, and I'll see you in the next lecture.